Hello there, in the last two videos I went over how to make fully procedural cities. But full procedural isn't always the answer, and sometimes you want handcrafted with procedural enhancements. Hence in this video we will combine the manual with the procedural, using building assemblies. Now to begin, it's actually pretty easy. Start by assembling your building like you usually do. The only additional thing you need to do is tag the meshes for the PCG graph. The untagged meshes will just spawn as is and will be mostly unaffected by the graph. Once you're done assembling the building, structure, or anything else really, right click and go down to the level submenu and create a packed level actor. You'll get two assets out of this, a blueprint actor and a level, which you can then use to create the PCG setting asset that we need. And if you open up the blueprint, you'll see we have all the meshes that you used. Now to actually create the PCG asset we need, right click on the level, go to Asset Actions, and create PCG assets from level. Now one important thing to note is whenever you make changes to the packed level actor, you will have to manually update the PCG asset by going to Asset Actions and clicking Update Assets. I hope this can become more automatic later on, but for now remember to update the asset every time you make edits to the packed level actor. Now onto the blueprint that will hold some variables and functions for a PCG assembly. Add a PCG component to the graph, and we'll go over the graph in a bit. Now two variables are needed, one to hold the data asset that holds all the meshes for the building type, and one for the assembly settings we created. I also have a third to act as the main seed if you want to reshuffle what's being generated. Which leads us into the three functions for better usability. The refresh PCG function to clean up and regenerate. These nodes are engine included when you add the PCG plugin. A clear PCG function to clean up components. And then a random seed function to randomize the graph seed and then refresh. And then in the construction graph, we have the random seed happen when the blueprint is added to the scene. Simple enough, now onto the graph. First, let's start with the core of the graph. Create a point at the original component. Next, match and set attributes to assign the assembly. This is where you would assign the PCG setting that you want for each building type. And then you could switch that out whenever you want a different building. And if you want to automate this process, you can even make it an array and then have the graph randomly select one from the list. Although personally I prefer control when manually adding objects, it's an option to keep in mind. You don't need to partition in this specific example since the blueprint only produces one building at a time, but I'll leave it there just in case. Next, we have a PCG data loop that will load the PCG data asset and copy the points in the assembly to the center point. Next is the filter setup that separates the points by the text you applied. As you go down the list, you'll see the various tags I've added to the building meshes used. The first floor walls, the regular floor walls, first floor corners, regular corners, the roof floor, and the random cut. And then finally the spawner that spawns everything untagged as it is without changes. Not every tag needs to be used in every building, and even if you were to leave everything untagged, it would still work just fine. As you can see here, with the data loop straight into the spawner, you can still get a building. And once the filters are reconnected, you get the building plus the additional effects of the graph. So let's go over them now. Now for the simplest thing, it would be the random call that randomly cuts a portion of the meshes tagged with that. Now for something a little more complex, let's look at the roof and the rooftop add-ons. First, you grab the roof floor points and match and set the roof meshes from the data asset. More on that later. Partition by mesh and feed them into an open back loop. Now, if you've seen some of my previous videos, highly recommended, you will find a lot of what you see here familiar. But let's go over them quickly anyway, since I want this to also stand as a standalone video. Now, what this loop does is it checks if the meshes have been marked as open backed, and then it will create a downward facing point for the ceiling. Then back in the main graph, they are assigned and both fed into a per mesh transform subgraph, which will then add any final adjustments on a per mesh basis before spawning. Next, we'll use the roof points to spawn any rooftop add-ons. First, we need to move them up a bit by the thickness of the roof. To do that, we get the roof mesh and use a new subgraph. The get bound subgraph is a set of nodes that take the mesh bounds and splits them up into a very reusable manner. It takes the bond min and max, subtracts them, and then makes them absolute. With that done, you can move up the roof points with a transform points. Next, we match and set the rooftop add-ons and partition by mesh. We scale up the bounds with a scale to bounds subgraph. Very similar to the bounds subgraph we used earlier. Next, difference with the roof walls to prevent anything from going over the edge of the building. And we will also reroute the height of the walls for later use. We then merge the points and do a random choice to select points according to our roof to building size ratio. Of course, since that involves the data asset, we'll go over it later. Next, partition by index, and then we do a snap rotation subgraph. To explain it quickly, create a snap degrees and snag segments attributes. Add a density noise to get a random value between 0 and 1. Get that density and multiply it by the snap segments. Round and then multiply by the snap degrees. We make that a rotator and add it to the transform points rotation. We then merge the points and repartition by the mesh. Then we do another mesh transform, this one a version 2 with a range of values instead of just one predetermined one. Finally, with that complete, we spawn the building rooftop add-ons. Now, let me explain the data asset that I've been using to save the meshes and settings for the graph. There are a lot of settings here that we haven't used in the assembly graph because the data asset is designed to be reusable and multiple different graphs. If you've seen the Procedural City videos, this is the same data asset we used to generate the fully procedural buildings. And in here, we're using it to help define our assembly building. Like the roof to building size ratio setting, which will decide how many rooftop add-ons to add on a building per its size. To make these data assets, create a primary data asset that will act as the parent. This is where you create the variables and add the mesh structures. Those custom mesh structures are what hold all the variables for individual meshes. This is where you find the mesh weight, which defines how often that mesh shows up, as well as other settings such as scale, offset, pivot adjustment, and whether or not it will spawn decals or additional meshes. Alright, now on to the second part. What I do here is create a spline from the bottom of the building to the top and divide it by the wall height. With that, we now have a way to automatically count how many floors are in each building. And we can use that to do a variety of different things on a per floor basis. But first, we need the necessary information. Combine all the points and create a get bound subgraph. This will get the overall dimensions of the assembly and create reroute nodes for those. Next, we also need the dimensions of the wall, so get mesh from point and get bounds again. Now we can create the points we need for the spline. One for the first floor above the ground floor, and the second is moved up by the assembly height minus the roof. Now we partition that spline and turn it into a loop for our copy points up. What it does is pretty simple. It moves up the floor points for each spline point and uses some settings from our data asset and map to divide those points into primary and secondary floor points. You can ignore the vertically alike setting in this instance, but everything else is just making numbers more random. Now then, move them slightly to sit in the middle of each floor. And we are done with that reroute. Now then, down to the walls. We match and set the wall mesh for the wall points and partition by mesh. We check for open back, do a per mesh transform, and spawn the walls. We can then offset the walls a little and add an external object loop graph. This loop graph will loop for each object in the data asset. Assign the mesh, adjust the bounds, and add a per mesh transform. We difference the incoming points from the previous runs of the graph, and do a front door check if you only want the front of the building. Then a random point select. Then below that we have the door for that earlier input. We don't do much with it besides extending its size to cover the front side of the building. Below that we work with the regular floor walls. This is where we split the regular floor walls with the secondary floor walls using the floor count. They then get partitioned, checked for open back, and add a per mesh transform. The corners that follow use the same formula, so let's move on to something far more interesting. The wall attachments. The wall attachments in the spawn and exterior for decals and vegetation growth. First, rename the growth decal spawning to just enabled, and then feed it into a loop subgraph that checks for that enabled. From there we get two spawn on exterior subgraphs, one to be used for the decals and one for the meshes. Make sure to get the exterior, the bottom floor, the assembly height, and the seed. Now, there are a couple things to go over since there's loops within loops happening here. First is the per object loop. This will take all of a singular object spawned and create a density using the distance from the first floor. What follows is some settings to filter out the points, as well as some settings to flip the density if you want to go from bottom to top or top to bottom, as well as an attribute read map to affect the scale, and some additional noise to keep things from looking too uniform. Now, what happens in the second loop is the mesh sampler that will occur on a per mesh basis. This is the graph that we're going to use to sample the mesh we're going to spawn on top of. And then it sorts out those meshes by rotation. And that goes into the third subgraph, which will filter out points by normal. This is important for meshes that have polygons facing inwards or in awkward directions. We don't want ivy spawning inside the building after all, just on the outside. First, rotate the point forward and use a point to normal color blueprint. That color is then used as the normal to density normal source. That is what we're going to use to filter. And we also have a material ID filter if you want the additional control. This material ID is obtained from the mesh sampler we had earlier. You'll find that down in the extras. It will sample the material ID and output that as a material attribute. And with that done, you can partition by mesh, add a per mesh transform, and then spawn. Although in the case of the decals, you won't be using a static mesh spawner, but instead a spawn actor, with the decal actor being the template class you want to target. Now with that done, we have our building exteriors completed. Alright, let's begin the second part of this and walk through building interiors. It's actually been about a week since I made the first part, so there's been some changes to the graph since then. The settings are now set up in a way so that the graph functions both by itself as a standalone, or as a loop within a bigger graph. Overall, the core of the graph hasn't changed, only more storing and retrieving of settings and variables has been moved to the data asset for modularity. Not completely yet though, I still wanted to finish this video up already, so I still have a few set up in the blueprint. Now for how the interiors are done. Figuring out how to do interiors is both really tricky to figure out and surprisingly simple to implement. But this is what I eventually settled down on, floor assemblies. And you can see here two different examples of floor assembly. The first one I made, very simple to start with, and then the second one with a little more complexity. But they're both pretty straightforward to build. Simply arrange your assets manually like you usually would, and tag the meshes you want to randomize in the graph. In this case, I kept it very simple and only tagged the floor objects, objects to random call, and one mini assembly. Now the core of this graph, as I said, ridiculously simple. All you do is take the unsplit floors from the auto floor count and pass that into the branch node. This branch node will count the number of floor assemblies in the data asset and automatically turn on if floor assemblies are detected. From there, we create a new loop graph called Building Interior Assembly. But first, we need to go over the changes to our data asset. Our now far more organized data asset now has categories for easier understanding, as well as a couple more variables. First, off the floor assembly list is where you put down the floors that this building type will use. And secondly, the find and replace mesh list. The find and replace list is empty at the moment with only a placeholder, but you'll see it in action better once we get to the mini assemblies. The mini assemblies, as per their name, are the same process as the floor assemblies but on a smaller scale. In this case, I do have an example set up with this closet here as a mini assembly. And the clothes hanging from it are meshes that have been tagged to be randomized and replaced. Anyway, now back to the graph. In the interior loop graph, get the floor and match and set the floor assemblies. From there, use the PCG data loop to apply the assembly to the floor and attribute filter two tags. Ignore the filter that takes out the floor. The sole purpose of that is to enable us to see through the building. Naturally, you don't want the floors to be invisible in your final result. Now, the first filter you actually need is the random call. This will take any meshes tagged as such and pass them through a select points. Then, those get joined back in the mini assembly filter. Those that are tagged as mini assemblies will get output towards the next subgraph, while the rest go through a tag search and replace subgraph. What this graph does is it goes through your find and replace list and replace the tagged meshes with a random mesh matching that tag. As an example, if you want to randomize the chair meshes that show up, add some new additions to the array and give them the chair tag. Now any object tagged with chair will be randomly replaced with one of these chairs. And you can continue adding more tag types to the array until you're satisfied with the variety you get. Now how does this tag search and replace work? All it takes is the attribute partition to split up the list by tag. Then in the loop graph, we go through each tag and match them with the tagged points. We also make sure to use the feedback of the unmatched points after the first loop to prevent the same points from being looped multiple times and creating duplicates. Then finally in the final loop, the remaining points that weren't matched with a tag will get output as is with no change. Now on to the mini assemblies, or the assemblies within the assemblies that will be within the assemblies. Now you'll find this graph very similar to the find and replace subgraph. First you partition by the assembly type, and then loop to filter and match the correspondingly tagged mesh. Now the reusable data loop graph will be looking for the attribute PCG Assembly, which is currently still holding our floor assembly, so make sure to overwrite that before feeding it into the data loop. After that, you can reuse the tag search and replace loop graph, just like in the floor assemblies, to find and randomize tagged meshes. With that done, feed the leave as is points directly into the mesh spawner, and the meshes that got replaced and randomized will go into the per mesh transform for any final additional adjustments. With that done, you now have interiors for your PCG buildings. Now, for those of you curious about this unexplained subgraph up here, it is one of my previous attempts to make interiors. I eventually decided that it wasn't worth following through, but just in case it is of interest to anyone else, I'll quickly go speed through it. To explain what it does, is instead of having to create the entire floor, you only need to create the walls and a few cubes that have been tagged with the info needed to fill in the room. Seems more convenient at first glance, but a lot more processing goes on in the background. Alright, first let's take a look at what we need. We need the room points themselves, the room types, the walls, the interior doors, the exterior doors, and the floors. Now partition the room types. The room types being an array for holding a pair of variables, a string, and a data asset holding the meshes for that room type. This data asset was a sort of prelude to the floor assembly asset list that came later. Now within the graph, you need to filter out the points by their room type and then partition by index. Now we can start cycling through each room point and start filling in the room. First, to figure out what the room actually is, we need to do a raycast to hit the walls of the room and get the distance from the cube. Then you can add the distances together and turn it into a vector to form a grid. Now that the grid for the room has been created, we also need to center it. Lerp the transform location and get the x and y into a vector with the floor z. Now the grid of points for that room will be placed on the floor and centered correctly. Now in the case of irregular room shapes, we need to start finding out which walls are actually connected to our room, and in which direction are those walls facing. So what we do is some pathfinding to find which walls we can connect to. Then to find which direction those walls face relative to the room, we have a graph that subtracts the location of the wall from the room center to create a rotator from X. Now we create two copies of those walls, rotated 90 or negative 90, and compare it with a normal to density node. The normal to density node compares the normal of the walls with the normal of the points facing inwards, and applies that as a density. With that done, we can now filter out which walls face inwards and which walls face outwards. And then depending on whether they were facing inwards or outwards, you can now apply the appropriate bonds modifier and restore them to their original position. Now we can start applying those walls to difference the grid. Now that grid will go through a set of transform and difference nodes to get the perimeter. Now we can start finally processing those points to spawn meshes. Turn the points inwards so we can start spawning objects that we find along the walls. Set and match with along the wall assets. Scale the bounds to the size of the mesh, and then per mesh transform. Filter out the mini assemblies and do a subgraph to get the bounds of the complete assembly. Then difference from the walls, and then set up a subgraph that goes through the various settings for that particular mesh or assembly. The graph will distance from the door. Then if you want a specific amount, it uses a random choice. Or if not, we'll self-prune and then select points. Also an additional filter for a setting called require at least one, so that mesh will have priority over other meshes. The ones that have been marked as such will then feed back into the must-haves feedback, and that will cycle back to the starting difference node. After that, we do some difference and self-prune to get rid of any last overlaps. And then once again, the assembly points get filtered out, and the rest goes straight into the static mesh spawner. Now for the inner room meshes, we use a distance node to pull them back from the walls. Match and set the interior room assets. Partition and scale the meshes to bounds. Per mesh transform. Then go through the process as below for the assemblies. We also have an additional graph, rotate it till it fits. A very simple graph that just spins things around. And then we bring back the mesh setting graph. Then the same as before, we use a filter to split the mesh and the assemblies. And then with that done, we exit the subgraph and follow through the process for the mini assemblies. And that is the room type method. It has some things I like, but overall the floor assemblies are faster to process, simpler to understand, and can fit more looks and building types than what the room types can handle. I think I'll still leave it in the project files in case someone else feels interested in it, but for now that finishes this video. And if you're interested in seeing the PCG City graph, you can check out my other videos. And if you want the project files, you can support the channel by getting them on either Gumroad or supporting me on Patreon.